Okay, it's my pleasure to welcome introduce Felix Janda here, who will be talking about enumerative geometry, old and new.
Thank you very much for the invitation and the introduction. Especially thanks for what said. And so today I want to talk about enumerative geometry, which is about counting the number of geometric objects. And for example, the most elementary enumerative problem is actually the first of Euclid's postulates, which just says if you have 2 points in the plane, there's one line through them. But today I will start by talking about 2 relatively classical enumerative problems, less classical than this one, and will show you how to solve them. And after that I will talk about a really modern problem that has been studied since the 1990s. It's called computing the Gromov-Witten invariants of quintic threefolds, and that I've recently made some contribution to after a lot of people have made some a lot of recent progress on this problem with my collaborators, but I'll come to that later. And so for now I want to start with 2 really classical enumerative problems. And the subject was kind of found by Schubert, who lived in the 19th century, and he had a paper in 1874, which is called, it's in German, it's called Colloquium, der abzählenden Geometrie. And if you put this into English, this would be calculus of enumerative geometry. And in that paper he kind of founded the subject. And one of the problems he studies in that paper is the following. So maybe let's make a problem. So say you're given 4 lines. Say you have 1 up to 4 in 3 space. How many lines L pass through? Maybe let me draw some. And for that it's good to have some pictures. So, let's say there are 4 lines, I maybe choose them randomly. So let's see. So we have like 4 lines and they don't intersect. I mean, because they're chosen randomly. And so let's maybe all 1, all 2, all 3, and all 4. Now the question is, how many lines can we find that pass through all of them? In that case, it turns out the number is not 1. But maybe the first thing you should make sure when you think about these problems is that enumerative problems, you want such types of problems which have finitely many solutions, so you can count them. And if you had only 2 lines, then you could connect any 2 points on these lines, and they would form, you would get a line that passes through the 2 given lines. And it turns out if you impose the condition that it passes through 2 more lines, you only get a finitely many solutions. And here the solution, and let me explain why, is 2. And I give you 2 different approaches to how to see that there are 2 lines passing through those. So the first way to do this, and both of the ways are kind of due to Schubert. And the first way, he uses something that Schubert calls a principle of conservation of number. The idea is, say you have a configuration of lines, and you found one line passing through them. What Schubert says is if you move these 4 lines slightly, you can also accordingly move this line passing through them. And what Schubert says is that because we know kind of the solution to these problems, they deform as you deform these lines, you can assume that the 4 lines lie in some special position that is easier to deal with. Namely, let's make the following assumption. Let's assume L1 and L2 intersect.
Oh, sorry.
If you have 4 random lines, they won't intersect. But let's make the assumption let's move them such that L1 and L2 intersect. And then I can actually draw for you where the two lines passing through them are. And so let me draw the first picture. So if you have 2 lines which intersect, they lie. Maybe let me use different colors for the different lines so we can keep track of them. Maybe let me use yellow for the 2 lines that intersect. So maybe L1 and L2. And now the other 2 lines, they're random. They will pass. At some point, they will pass through this plane, but they won't lie in it. This. Something like that. And now what you do. And now you can find the line. What you just do is you connect these two. You connect these 2 points where the line 3 and line 4 intersect the plane. And you can see if maybe if you assume these are not parallel, they will intersect all the 4 lines. Okay, that's solution 1. And solution 2. So let's see, we still have L1 and L2, they intersect. But now what you do is, maybe we take L3, and you pick the plane such that the plane contains L3. And the plane contains L3, and it also contains this intersection point. So maybe now this part is below the plane, this part is below the plane. And now the green line lies in the plane, and the intersection point lies in the plane. But kind of only half of each yellow line lies inside.
You can see from here, sorry.
Oh. So now it's a different plane. The plane in which ML3 lies and in which the intersection point lies. Right, we can, so this guy, we can put the plane such that it passes through one given point. And then if we take the last line, which is blue, it will somewhere go into the plane. And what we do now is you connect the intersection point. Okay. So for the second solution, you pass through the intersection point and you pass to the point where the blue line intersects the plane. And you can check that these are all possible solutions. And now Schubert says, although we assumed two of the lines intersected, if you move them apart from each other, you can deform this, you can move this purple line such that it still passes through all of the 4 given lines. Okay. Questions? Okay. And okay, maybe it. So actually, let me say so. It takes some work to make this rigorous, and I'm not going to do it in this talk. And like one of Hilbert's problems was making what Schubert did rigorous. Let me go to the second one. which is nowadays called Schubert calculus, after the name of this paper. And what you do here is kind of transforming this geometric problem into a computation. Let me show you how to do that. The idea, maybe that I should say one thing before I move on. Here I was a bit imprecise what I mean by lines in 3 space. In the remainder of this talk, it is useful to work over the complex numbers. So each of these lines appeared as a complex line lying inside MC3. That's because, like in finding solutions to the enumerative problems often was solving polynomial equations, and that's much easier if you work with complex numbers. And, but I mean, for now you can think we still work with real numbers if it's nicer for you. And also, it is useful to compactify everything, to work with the complex projective line, which is, I mean, the Riemann sphere, where you add a point at infinity. And like to compactify everything, you replace 3 space by complex projective 3 space. I mean, that has like the advantage that if you have the complex plane, then you know that any 2 lines they intersect. You don't have parallel lines, you don't need to worry about that. Like it also removes some technical issues. But if you prefer, please continue thinking about real lines in real space. But for the second way, the idea is to kind of look at this problem systematically. So what we are trying to find are certain lines in 3 space. And so what you do is you first look at the space of all lines in 3 space. Or you can take R3 if you prefer. And the space, I mean at first it's a set, but there's a natural topology and you can put on it. And you can even make it a manifold, which is called the Riemann GR13. Which is so now if I use complex numbers, will be a complex 4-dimensional space. It's a complex manifold of dimension 4, so it's real 8-dimensional. And okay, so that's like just generally thinking. Just generally want to think about lines in P3. You look at this Riemannian, and now the question is how to incorporate this condition that the line. This line L should pass through these 4 lines. How to incorporate that? And you can kind of do it step by step. And so you set up a set HI, which sits inside here, defined as a set of all lines which intersect. I mean, like you can, for each I between 1 and 4, you can define a set MHI, looking only at lines which intersect with this given line that the complex that the Riemann gives you. And now you can check that the condition to pass through the line Li, that gives you a complex codimension and 1 condition. It gives you like 1 condition on this line. And so you can see if you impose maybe, let me see. So, right, the thing we are interested in are the lines which pass through all of the 4 lines. So what we're interested in is the intersection of all of the 4 of them. And the question is, what is the number of elements in this intersection? Okay, and now if you look at the dimension, you can see at least the dimensions seem to work out. If you intersect 4 things of codimension 1, it should inside the 4-dimensional space you should get something of dimension 0. And so this should be a finite number of points. And so we hope to show that this number of points is 2. And okay, so this is what we want. And so now yeah, if you know enough complex numbers, it's now easy for you. So what you need to, so now to do the actual calculus, you move to cohomology, and you take the cohomology class of each of these, and what you like take the cut product of all these cohomology classes, Poincaré dual cohomology classes, and you get some top dimensional cohomology class. You take the degree, and you get some number, and that's actually a concrete description of the cohomology of the Riemannian. You find the number is 2. But yeah, and what nowadays is called Schubert calculus. It's mostly doing computations in the cohomology of Riemannians in general, and that one's explicitly known, and nowadays it's mostly about the combinatorics of doing the computations in the cohomology. Okay. So I think that's what I wanted to say about this first problem. If there are no questions, I'll move on. Problem number 2. Maybe I should draw a picture as well. Well, CP1 we can also think like it's like this here. Okay. So we are looking at spheres lying in this 3 space. And now we're going to move up from spheres to tori, complex tori. And it's going to be, and the problem is going to be outside of Schubert's work. Schubert's work is mostly about studying things like lines or maybe conics. But so the next problem, I think I should first say that maybe let's just say, let me say something as many of you know about elliptic curves. So first, usually, I guess the elliptic curve is given by some, they're given by some Weierstrass equation. They're given by some equation in complex 2 space, or maybe CP2. And if you draw the real picture, I guess it might look something like this. I've here just drawn given the equation of an example of elliptic curve. But if you look at it's like, but if you, we should work with the complex numbers, so elliptic curve looks like a surface, and they turn out to correspond to genus 1 surfaces. Maybe over here. And for the problem I will talk about, it's not so useful to think about the equation of an elliptic curve. It's more useful to think about it the following way. Like to get a torus, you can start out with a parallelogram, and you identify opposite sides using translations. And because translations are holomorphic, that gives you the structure of a Riemann surface, the complex one-dimensional manifold on this torus. Okay, that's one way to think about the curve. And an even better way is to think about it the following way. This parallelogram, you put it into the complex plane. And if you take all the corners of this parallelogram and you take the lattice span plane, some kind of lattice, lattice gamma, and then you can describe the elliptic curve as the quotient of the complex plane by a translation using this lattice gamma, elements of this lattice gamma. And the possible elliptic curves, there are many possible elliptic curves, and they're classified by what lattice you take. And what elliptic curves you take, it doesn't really depend on what parallelogram you choose, but it only depends on the lattice. Okay, but so now what is the second problem? So say you're given E. So you give an elliptic curve E. And what is the number of degree D powers of E by another elliptic curve? And let me call it C. Let me say in other words, we are trying to count the following. To fix this curve E, we're trying to count the number of C, which are also elliptic curves. And together with a map from C to E, which is the power of degree. And let me now, the problem depends on what is the degree you choose. And one can check that this problem makes sense for any degree, you could say. Like that for any degree, there's a finite number of these. Like for example, n1 is equal to 1, like which is the number. I mean this 1 corresponds to the map from E to. It's the identity map from E to D. Okay, but if you have higher degree, there are more possibilities. And there's some connection to modular forms here. Yeah. And yeah, let me just tell you the solution. Namely, you can characterize this set of covers of E just in terms of this lattice. And say E is given by the lattice gamma. Then what you're looking for is just sublattices. So you're looking at the number of gamma prime and sublattice of sublattices of E. I'm sorry, sublattices of like such that if you take the quotient of like the index of the sublattice should be index D sublattices. Like for example, if you wanted a degree 2 sublattice, you could take the sublattice. We could take we could add in all these points to the lattice, get a sublattice. Okay. But anyway, my point is there's a concrete formula for this number of sublattices, and it's just the divisor function of D. So which is just the sum of divisors of D. And so for example now n2 would be equal to all the sum of all the divisors of 2, so like 1 plus 2. Okay. And now I guess you can call this as a solution to a problem. And actually you get a maybe even nicer answer that you can maybe write down like using just a formula. If you put all these numbers into a generating series, put all of them together. And namely, if you now take the sum over all the NDs and you introduce the formal variable q to the d, and if you put in some factor d here to make the answer nicer, then what you get is just minus 1 over 24 of the logarithm of the modular discriminant, or to be precise, the Fourier expansion of modular discriminant. precise, there's some extra thing here. Can maybe ignore. Yeah, so it turns out for many enumerative problems, the answer is related to some kind of wonder forms.
The modular discriminant of what?
Just SL2C. This classic one. Classic. I mean, usually this is set in terms of the eta function. And right, if you replace this by the eta function and remove the 1/24, it will be the same. Okay. So after, yeah, no more questions? Yes.
What's E? E is fixed by a given lattice gamma?
Yes, yes. So E.
But then D does not depend on.
The answer does not depend on the lattice. The answer is the same for any elliptic curve. This is similar to earlier. The answer did not depend on the exact position of the lines. Also true. And here it even doesn't depend on which elliptic curve you take. Like often the invariants stay the same if you change the parameters smoothly. Okay. So after these two problems, let me go to the modern enumerative problem that I've personally studied. And to go to there to make some connection, let me first just go back to the first and the second problem and like compare them slightly, very, very roughly. In the first problem, we were interested in lines, which is CP1, in CP3. And instead of looking at them as a subset, you can think of them as that we looked at CP1 spheres mapping into complex free space. And in the second problem, it's about some curve, not fixed curve, mapping to E. And now, if you want to generalize these two things, you will see in general we can look at a genus G, Riemann surface. Okay, and so right, these are both Riemann surfaces. And on the other hand, this is kind of the source of your map, and the target of your map can be kind of anything. Like here, this is some target, which in these two cases it's some complex manifold. Okay, and now the common generalization of these two problems is what is called Gromov-Witten theory. So there you define the following numbers called Gromov-Witten invariants, which they depend on two parameters, G and D. So G is the genus of the Riemann surface, and D is the degree of the map. So here the degree would be for 1, maybe genus 0, degree 1. Here genus 1, degree. Okay. And here, if you have some target complex manifold X, you can look at the number of all Riemann surfaces. Genus G, Riemann surfaces, or in other words, complex algebraic, smooth algebraic curves of genus G, and together with a map from C into your target X, it's up to isomorphism, or up to you identify maps. I mean curves. Maybe let me leave this out. Just count the number of maps. I'm putting in the rack many subtleties, and I mean most importantly.
Where's D? You wrote a D.
where's D? Thank you. and yeah, actually D should be actually a cohomology class in X. And then we just say informally the degree of M is equal to D. I mean, actually D should be a curve class in X, and it's the homology class of the image of C in X. And you fix that. But most importantly, in many situations, the Gromov-Witten invariants are not an actual count of the number of these objects. It turns out in some situations where you would expect this is a zero-dimensional space, it still has infinite remaining spaces. It's kind of bad. But in some situations, like the two situations we talked about, the Gromov-Witten invariants agree with the actual counts of curves. But so why would you study these invariants even if they do not solve any actual enumerative problem? So there are many motivations, like I guess here there's Gromov-Witten. So maybe not exactly from Gromov's point of view, but I mean Gromov is kind of in symplectic geometry. And one motivation is, here you can actually allow a symplectic manifold and take F to be a so-called pseudo-holomorphic map. But anyway, one of the initial motivations was to use these invariants to define invariants to view these as invariants of F, as symplectic invariants of X. And to say if you have like different curve constants on X and Y, you can see that X and Y must be different from each other. But there are many other motivations, like sometimes they're like beautiful connections to modular forms. And you can also define what's called quantum cohomology, a deformation of the cohomology ring of X. That gives you sometimes interesting combinatorial structures. Or for example, if your target is, it can also be related to quantum groups if your target is equivalent variety. But the definition of Gromov-Witten invariance is kind of technical. It involves doing homology computations on very singular spaces. And I won't be able to give anything close to a precise definition here. But I should say, so I mentioned Gromov, and also there's Witten here, because in the early 90s, the subject kind of really started out because physicists, Witten's a physicist, they computed Gromov-Witten invariants and used that to give predictions on some classical enumerative problems. And so I've said something about Gromov-Witten theory. And to get more concrete, today I want to talk about a very special target, which is called a quintic threefold. So that's just a quintic hypersurface. It's just a quintic hypersurface. So it's given by a quintic. It's a locus inside complex projective force space, given by the zero locus of a quintic equation in the variables. And it's called threefold because complex dimension is 3. And why we study this particular manifold is because of its very special geometry. It's an example of a Calabi-Yau threefold. So meaning it has a one-dimensional space of holomorphic three forms. And it has a very special geometry, and it's also been studied a lot in string theory because string theorists use, like in string theory, people look at a 10-dimensional space where 4 of the dimensions are space and time, but there's 6 extra dimensions. And the 6 extra dimension is supposed to be kind of small, and we can't observe it in real life. And so these 6 dimensions, they're supposed to, in order to get a consistent physical theory, these extra 6 dimensions, they need to form a small Calabi-Yau threefold. And because of that, string theorists are really interested in finding many examples of Calabi-Yau threefolds in the hope that one of them corresponds to our real life. Okay, now the problem is just compute. Did I write it down? Yeah, so compute this Gromov-Witten invariant of this spectral manifold. And so I should also say, and Calabi-Yau theory manifolds are also special from the point of enumerative geometry, in the sense that you can raise the question of asking, have the dimensions work out no matter in what genus and in what degree curves mapping to the quintic you're interested in. Like this problem is supposed to have. It is expected to have finite many solutions for any of these parameters. And so I have like a large number of invariants depending on 2 parameters. Okay, and let me also say that, sometimes these are very classical. So for example, the number n01 or certain of x5, it turns out it agrees with the number of lines, complex lines on a quintic threefold. Like this virtual number is actually the actual count of lines. And that one was computed by Schubert. In the same paper as I mentioned in the beginning, it's 2,875. And you can use Schubert calculus to do this, because it's about lines. So look at the Riemannian of lines in complex 4 space, and then you impose the condition to lie on a quintic. Okay, but the actual number of surfaces on X5 we only know in very few examples. But the Gromov-Witten invariants are much more tractable. And so, for example, what is known as by the very influencing work of physicists, Riemann and Parks in 1991, they computed what they call F0. It's a generating series of all genus 0. Say you fix the genus to be 0, but you look at all degree Gromov-Witten invariants of quintic threefold, and they give an explicit formula for this. But okay, I guess it's in physics, so it was only a prediction. And later, like a lot of, they were able to compute, they were able to predict some more of these actual enumerative invariants. So people got interested, they got interested how could physicists compute these numbers that mathematicians hadn't computed before. And
you can times q to the d.
Yes, thank you. Yes. And so mathematicians intensively worked on this problem. And then in the 90s, Young, and Yau proved the so-called mirror conjecture, which established this formula. And I guess I should say it's called mirror conjecture because this formula is related to periods of a family of manifolds called the mirror family of quintic threefolds. There's a whole subject of mirror symmetry that in mathematics that came out of this work. A lot of details. Okay. but it's genus 1, and it's genus 0. And then in physics, soon after that, they already had formulas for computing the analogous function genus 1. Maybe not right. I mean, it's the same thing, but with genus 1 instead of genus 0. And then again, and then it took mathematicians quite a long time until Alexei solved the problem. But it took quite a time. Like I think, like middle of 2000.
Awesome.
And he got some help. It's kind of a large project. I mean, he also proved some more general results about genus 1 invariants, and not just for quintic threefolds. Anyway, it took a lot of physics. They were quick with. Like the problem is like the definition of these is very subtle and like it's not very explicit and it's difficult to get hold of them. And so in PCOB, they're the same paper. They also did genus 2.
PCOB?
Yes.
Who?
Ryshatsky, Sisotti, Oguri, and Barker. Yeah, this paper is really famous.
So physicists learn against initials.
I mean, yeah, I can write it out, but I can't spell this one.
I can help.
I can write this one out. I'm sorry. Awesome. Green. They're very, very famous paper. They did the same thing. And so what I'm doing and what we've essentially done is some more details to work out with Yongbin Ron and there's some geometric part with this, which is with Chida Chen, and some computational part that is with Schweigel, and where we compute the invariance of genus 2. And I should say more. I mean, now you should go on, so now we can go genus 3, genus 4. I mean, could ask about how to move on, but maybe I should say, so the I mean, each of these has some format. I'm not writing it down because they get kind of more and more complicated. And you can ask about what is the general, what can you say about the structure of, like, when the formulas get more and more complicated, it's maybe better to look at what are the common features. And for that, there are many predictions for physics. For example, there's something called polynomiality, which tells you that you can write fg as a polynomial in terms of five concrete series. These are like 5 power series which have concrete expansions. And this is not a random power series, but you can write it as a polynomial of them. And they are, again, related to periods. They can be written in terms of periods on the mirror manifold. Explicitly, but I don't have time. So, and if you know the degree of this polynomial, what it does for you is you go down from an infinite computation, where you need to compute the invariance for, right here there's an infinite sum, you need to compute the invariance for all the degrees. But if you know polynomiality, if you know the degree of this polynomial, you're down to find infinitely many coefficients of the polynomial. And I should also say this is also sometimes called modularity, because this ring is similar to a ring. It's kind of analogous to a ring, to what you get for modular or quasi-modular forms. They like infinitely generated ring. And yeah, in physics, I mean, they're actually supposed to correspond to some kind of modular forms, but for a spin group, as before, I think. Anyway, these are predictions from physics. They're more or less so-called holomorphic non-equations, which tell you more about the coefficients of these polynomials. And then there are some more. And all these predictions have been used very successfully in physics. And what they can do to you is they reduce computation of Fg to computing finitely many invariants and small of them, about 2 to the minus 2 over 5 invariants for every genus. It gives you some inductive procedure which depends on some initial conditions. Maybe that's similar to solving a differential equation recursive by some series expansion recursively. Okay, and I hope you will see this number soon again. And then the physicists, if they use one more, I didn't tell you all of them, but if they add one more to them, if they use the classical algebraic Castanova bound, if you just use these structural results, you can compute very many Colloquium invariants. You can compute Fg. You can compute all degree invariants. And for all G less than or equal to 51. It's like very large and little. And that's kind of impressive, but okay, we're not there yet. Yeah, I want to, and we hope that the methods we use can be used to do this part of the predictions, not this. And I hope to explain why we expect that. But let me say that there are also other groups working on these problems, which also have recently made some success. And namely, this result has actually already been proven by work of this in math. Has been proven by work of Chang, Li, I think it's Chang, Guo, many authors. But okay, I can't talk about this today. But it's credit. Okay. Okay, but questions on.
Is that the same quo as over there? Is that the same quo in the two different groups?
Yes. That's kind of it's the same goal here. It's good at computations. It's good. But so yeah. So now let me tell you a bit about what's the difficulty of dealing with those. And, why can we compute them in genus 0, or why can't we compute them easily in higher genus? So the computation of invariants of x5, kind of all the methods are, or maybe at least most of the methods, is based on what is called the quantum methods principle. What that gives you is a relationship between the Gromov-Witten invariants of before. It determines for you from those the Gromov-Witten invariants of the space we're actually interested in. So here P4, that's our ambient space. It gives you a relationship between the invariance of the ambient space to the invariance of the hypersurface. But before I move on, I will say something here, namely, it doesn't work. It usually does not work. It only works unless, and I will tell you in a minute. But I should say that these ones, P4 is a much nicer space. It has a large torus action, and these invariants can be explicitly computed, although it takes a lot of. That's why you need people to do computations. This guy can be, in principle, computed via a method called material localization, or some generalization of this classical material localization. I mean, this was already done by Kontsevich in the early 90s, how to compute these. And if you're able to relate those, which are much more difficult, to invariants of P4, then at least you have some method of computing. Like the definition of confit invariance is very explicit, and you're happy about any way of getting a hold on that. But there's some issue with this principle. It doesn't always work. It works unless there exists, unless you can find curve, genus G curve with a map, such that an obstruction space does not vanish. It's you take the space of first check homology of the pullback of f of 05 on P4. And I make that more concrete, but using seriality, we can write this also as the space of sections of omega c, f of O minus 5. Or maybe I need to take dual. But let me make, such that, yeah, this is non-zero. But let me make this slightly more concrete.
Wait, so you're saying if that's a non-zero, then you cannot do this?
Yes, exactly. And maybe you can see why it works in genus 0 from here. Like the point is like on the Riemann, like in the genus 0 guy, you don't have differential, like holomorphic differentials, and like that f of star or minus 5, it only makes things worse. Namely, the condition you need is that like you have a problem. You have a problem if there exists eta not equal to 0, holomorphic differential. Differential on C. Vanishing with order 5 along each intersection. Of C with a hyperplane, fixed hyperplane. And maybe let me draw a picture. So I mean, to be precise, we're actually now looking at maps from C into P4. And now you fix some hyperplane, and this is like C. And we're interested in finding holomorphic differentials on this Riemann surface C, which I've drawn one-dimensionally here, which vanish with order 5 along each of those intersections. And if you can find something like that, then there's a problem with this principle. And if, so I didn't mention, but it is very important in Gromov-Witten theory to allow also singular curves. But if the curve is smooth, then this only happens if 5 times the degree. And this is the number of, D is the number of intersections with the hyperplane. It's less than or equal to 2 to minus 2. because the differential on a genus G Riemann surface is 2G minus 2 zeros. And so, because we impose all of these conditions, we need the genus to be large enough for this to work out. And so, equivalently, we write this as D being less than or equal to 2G minus 2 over 5. Okay.
So you're saying there's roughly 2G minus 2 over 5 kind of bad cases.
Yeah.
You can push those things.
Yeah. I mean, if I do it like this, it would seem maybe that genus 1 is kind of trivial. But like the point why everything is so complicated is because C usually has many components. And there can be there can be curves. Euclid surface could have several components. And maybe if on some of them has a large degree, you're fine. But if on some of them is degree 0, this guy is bad. And this guy is bad. The principle fails. And okay, I think I'm almost out of time, so let me say in words what we do. So I mentioned the two kind of works. So with Chen, what we do is we construct new moduli spaces, which we use to kind of separate out these contributions from each other. What we do is we produce a formula which will express the Gromov-Witten invariance of the quintic as a sum of a main contribution and contributions of each of those bad loci. And the contribution of one bad locus like this will be here kind of the So here, in these cases where we have trouble, they give rise to something. The contributions of these bad loci give rise, for smooth curves, give rise to something we call effective invariants. These are invariants which we can define, but we don't know how to compute them. But they're just numbers, and there are 2G minus 2 or 5 of them. And what we do in our paper, I mean, we define these invariants, but also we show that you can write the contribution, you can separate the contribution to the Gromov-Witten invariant in terms of a main contribution and a contribution of each of these bad loci, where these bad components give rise to the corresponding effective genus. This will give you some effective genus 1 invariant. And this guy will give rise to some Gromov-Witten invariant of T4, which we can compute. Like in general, there's going to be a lot of combinatorics, like the different possible components and intersecting with each other and possible degree distributions. But for each of them, you get it in terms of something you can't compute, but which is a finite amount of information, and something you can compute. And like what we do in the work with Calabi-Yau is that we show that the contribution of these non-bad components, their generating series satisfy, for example, rely in these rings of 5 generators. So that then what these invariants we can't compute will do, they only change the coefficient of these modular forms. Like you can prove that something is a polynomial without writing down the actual polynomial by showing that it's like it's like a linear combination with unknown coefficient of something you know is a polynomial history. And in genus 2, it turns out, if you look at this condition, there's will tell you there's only one invariant we can't compute, but there's some different way we can compute there's some completely unrelated method we can use to compute the invariant. We can use that to write down F2. And I think I should stop here. Let's wait.
So just to clarify, so for genus 2 you can compute F2,
Yes.
and for higher genera you get some structure theorem or something?
Yeah, so I mean, issues we haven't written. I mean, there's still some technicalities to figure out. Like we haven't really finished. We've already constructed a modular space, but we haven't done this decomposition, figured out we kind of have some rough idea how to do everything, but we haven't figured out all details. And with Schweigor, we've done computations depending on a formula we still need to justify. And so genus 3.
Yeah, you can look at genus 3.
Genus 3 we could do in principle, but it's much more complicated, and we prefer to first improving the structural results. And if you use the structural results, the computation gets much easier.
But that number is 0.
Which number is 0?
2g minus 2 divided by 5.
Yeah, so what the physicists, they also use here, they use degree 0. In general, we can compute degree 0 Colloquium invariants.
You can also compute degree 1, I'm sure.
Yes. If you have some other way like that, if you have some other way to compute degree 0, degree 1 invariants, you can combine the methods and it will give you more. You can compute it for more genera than before. Yeah, like all information you have about Gromov-Witten invariants, you can use it to solve some of these constants, and then you can compute more genera. Like because of this modularity, the computing finitely many invariants gives you a computation of infinitely many invariants. If you get one more genus, you get really all the invariants in the genus for any degree. Okay. More questions?
And this type of structure is only for quintic threefolds, or what kind of Calabi-Yaus?
Yeah, we expected kind of wiry Calabi-Yau.
Sorry?
We expected for any Calabi-Yau. If you don't have a threefold, you need to form generating series slightly differently. But then we say we expect the story to be true kind of for every Calabi-Yau threefold.
But does your
Our method doesn't apply to it. Our method is related to this quantum Lefschetz principle. So what we need is that you have some nice ambient space, and you have a hypersurface, so the complete intersection at nice ambient space.
Then you need something like Picard number 1, or?
Yeah, like otherwise. I mean, we've only done one computation so far. For Picard number 2, probably it's still it's just going to be much more complicated. Principle.
But a 3-3 complete intersection in P5. I mean, for
Yes.
other Calabi-Yau complete intersections of projective space.
We want to do those.
Okay.
This takes time. Yeah, but this is one of the next natural examples. Yes.
So this computation for G less than or equal to 51, you have no idea how to sort of attack that problem in the math world.
I mean, like this Casanova bound. I mean, we expect that one can prove this last prediction they use, but we expect it's better to use things like DT, Donaldson-Thomas theory, or like we expect this more like a sheaf. This should be proven using sheaf theory.
There is a purport of Alexander Doan.
Okay.
But it depends on something which turned out to be not true.
Oh yeah, I know this preprint. Okay. Great.
Not true yet.
Okay, let's thank the speaker.